4, Oscillations. Enter the lab 4. In this experiment, I will observe and model the oscillating movement of a spring using the tracker application as well as web Python coding respectively. By applying Newton's second law and the energy principle, I will answer the prompted questions. The tracker portion. The mass of the spring ball was given to 0.402 kilograms. The starting frame was frame 22. This is where the ball is released. The frame rate was 10 frames per second, which is very unusual compared to the 30 frames per second typically. The elapsed time from frame 22 to the end was 5.7 seconds. Finding K. To find K, you need the period of oscillation formula, where T equals 2 pi multiplied with the square root of m over K. As you can see on the right side, there are 3 oscillations, and in the 3 oscillations was a elapsed time of 4.588 seconds. I took the average and I got T equals 1.52 seconds. From this point on, you can reformulate the period of oscillation formula to get K equals m times 4 pi squared over T squared. I plugged in the known quantities and I got K equals 6.875 approximately. Finding LO. At a length of 0.7 meters from the spring's origin, the spring was at equilibrium, meaning the combined forces were at 0, which also means spring force plus gravity force equals 0. This also means K multiplied with the difference between L minus LO minus M times G equals 0. You can reformulate this equation to get LO equals L minus mg over K. I plugged in the known quantities and I got LO equals 0.127 meters. Here's my code. I don't think it's really important to go over the code, as all the variables and expressions in the code were derived from the Newton's second law and the energy principles that we learned in our lectures. Here are the results of my program. As you can see, the energy versus time graph was correct, and the exposition model versus experimental model were relatively the same. However, the experimental model was a little bit more jaggy compared to the model derived from the computational model. The Y position model versus the experimental model was basically the same. What does it mean? Is the energy principle satisfied? Yes. Energy principle is delta E equals W. Since we include everything, including Earth plus spring, in our system, our work is equal to 0 because everything is in our system, which is delta E. Since work is equal to 0, delta E is also equal to 0. Delta E is equal to delta K plus delta U graph plus delta U spring, which is all in terms equal to 0. As you can see on the right hand side, throughout the graph, all the components of delta E balance to 0, satisfying the energy principle. What does it mean? Oscillation in the x direction versus y direction. As previously estimated, the period of oscillation for the y direction was 1.52 seconds on average between 3 oscillations for y positional data. For x position, 3 oscillations occurred in 4.938 seconds, 1.646 on average. So the oscillation for the x position was slightly higher than the oscillation for the y position, but in the end, they're very similar. The differences may be due to tracker error. As you can see on the right hand side, the y positional data is a lot more smoother than the x positional data. The x positional data is very ugly and very shaggy looking. As you can see on the curves, there are very sharp points and turns. This may be due to the small, minute changes in direction for x compared to the y. Because the directional changes are so small, tracking them with human hand became very difficult, resulting in a poorer looking graph, resulting in the minute difference in oscillation compared to the y positional data.